Welcome to today's lecture of Scalable Data Science. Today we will talk about frequent elements again, and we will see a different data structure today, one called count sketch. I am Anirban and I teach computer science and engineering at IIT Gandhinagar. So, we do not need much revisiting of the streaming model, but again we are dealing with both arrival only and arrival departure streams, and we are looking at the questions of frequency estimation in one pass. We have seen two algorithms until now, three algorithms until now actually. We have seen two deterministic counter based algorithms, the Mishra-Gries and the space saving, right, that work only in the arrival only setting. We have seen the count min sketch, that is a proper sketch that works in the arrival only setting, and the slight variant of that, let me call the count median sketch, right, where we say that we could take the median when we are returning the estimate, and this works in the arrival plus deletion. Okay. Although we did not quite see a proof of this, it is very similar to that of the count min sketch. So recall, before we go on to our new algorithm, let us recall what the count min sketch was, right. So, we are here we are using two parameters, one named w and the other named d, right. W are the different w hash functions, and d is the range of each of these hash functions. Okay. And then what the count min sketch would do is that it, given a particular update, it would look at where each of the hash functions places that element x, go to the corresponding cell and update the corresponding cell. That is all. Okay. So, the count sketch is actually something that is very similar, right. So, we have the same kind of data structure, we have a small summary w by d, right. There are w hash functions, right, h1 to hw, each of them map to the range 1 to d. There is also something additional, right. There are w sign hash functions, right, g1 to gw. Now, each of g1 to gw gives you a random sign for each element of the universe. So, think of it as flipping a coin for each element of the universe. If the coin comes out heads, you give it you assign it a sign +1. If the coin comes out tails, you assign it a sign -1. Okay. And of course, the hash functions h1 hi implicitly sort of assign given any particular element, it assigns it to one of the positions uniformly at random, right, with probability 1 over d. And again, what we will point out today, which we did not, I guess, do last time, is the fact that while we do the analysis for completely random hash functions, we could as well have used k wise independent hash functions for actually k to be equal to log 1 over delta. That is why. In fact, here we will need a smaller value of k. So, let me erase this. Here we actually need k to be 4 wise independent. That will actually be enough. Okay. So let us see. This is actually the count sketch. Okay. So, we do the initialization as expected, right. We initialize we choose h1 to hw, we also choose g1 to gw, and then we initialize the array A to be all 0. For any item and its update x and the update c, which is one element of the stream. So, here is what we do now, right. You look at, for each of the hash functions, you look at where that hash function is placing that item. You go to that cell. Now, instead of updating it by c, you multiply c by the sign gi of x, right. So, this becomes either plus c or it becomes minus c, right, and you do the update of that bucket with this sign, right. So, remember that each element gets only one sign, right. The next time the element comes, you again get the same sign, because this is a hash function. This is not any random variable that we are sort of conjuring up every time a new copy of the item comes. So, this is a hash function that assigns a sign to the item, and you always do a plus C or you always do a minus C if the update is C for that particular item. Okay. So, now what do we do when we are trying to answer the query, right. So, we look at, now again we have W estimates, right, 1 to W, I equal to 1 to W. So, and each of these estimates is now G I of x multiplied with A I comma H I of x. So, why are we pre-multiplying with G I of x? That is fairly obvious, right, because if G I of x was minus 1, you want to get rid of the minus. So, you again multiply it with G I of x. So, that is fine, right, but now we are taking the median of these estimates instead of taking their average, right, and we will see that is useful. Okay. So, as is our tradition, let us run down a small example. So, we have this stream and we have encoded the hash table, the hash functions in this format. So, what it means is that H 1 maps blue to the position 2 and G 1 maps blue to the sign plus. H 1 maps yellow to position 3 and G 1 maps yellow to the sign minus, and so on, right. So, the tuple denotes the first element of the tuple is the position to which H 1 is mapping the particular element. The next element of the tuple is a sign that says that what is the sign that the corresponding G function is assigning to this element. So, let us number the positions 1, 2, 3. Okay. So, first blue comes, so first red comes, red goes to 1 with plus and red goes to 3 with minus. Blue comes, blue goes to 2 with plus and blue goes to 1 with plus. Then 2 reds come, 2 reds go to 1 with plus and here with minus. Turquoise comes, turquoise go to 2 with minus, turquoise goes to 3 with a plus. Blue goes to 2 with a plus, 1 with a plus. 2 reds come, again go to 1 with plus and 3 with minus. 1 blue comes, goes to 2 with plus, goes to 1 with plus. Turquoise goes to 2 with minus, goes to 3 with plus. Yellow goes to 3 with minus, goes to 2 with plus. Blue goes to 2 with plus, goes to 1 with blue goes to 2 with plus, blue goes to 1 with plus. Okay. So, therefore, in the cell 1, right, here the total count is 5, here the total count is 1, 2, 3, 4 minus 2, 2. Here the total count is 1, 2, 3, 5 minus 2, 3. Here the total count is minus 1. Here the total count is plus 1. Here the total count is 3 minus 1, 2. Okay. So, that is how the data structure is going to look like. And how you answer the query is fairly obvious, that suppose you are queried with W, then in that case you go to position 3, you multiply it with minus, so that becomes minus 1 times 1 and then you go to position 2 of the hash bucket, so that is 1, and then you multiply that with a plus, because Gi is plus here, so plus 1. So, median of 1 and 1, and so we get a 1 here. So, at least W, I mean for yellow it is answered correctly, which is of course not the case for all the other elements. Okay. So, again the same kind of guarantees for the space as well as the update time, right, because each item is mapped to one bucket per row. So, it is not a surprise, that that you get the same kind of guarantees. The same, so the question is that what is D and what is W, right? And again, following the principle that we had, that in order to set the values of D and W, first you have to do error analysis, right? And based on the error analysis, you want to see that what is the dependence of W and D on the two typical error parameters, the approximation factor epsilon, right, as well as the error probability delta. Okay. So, let us start by setting D equal to 2 by epsilon square and W equal to log 1 over delta, right. So, then the W is let us denote y 1 by 2 y W as a W estimates. So, the ith estimate is this particular quantity, right. It is equal to, you look at the ith hash function and that gives you the cell A I H I of x. Okay. So, you multiply this cell by the sign hash G I of x. Okay. That gives you the ith estimate y I, and what are we doing at the end? We are returning the median of the ith estimates. Okay. So, let us at least calculate the expectation of each of these estimates. So, the expectation y I is nothing, is exactly this expectation, because that is the formula, and now I can expand out the A I H I of x in terms of the sum. So, what is the sum? It is nothing but you look at all the y that have appeared in the stream, right, and those y's that the hash function puts in this bucket, right, that the ith hash function puts in this bucket. You look at exactly those y's, you look at their signs G I of y, and then you get a weighted sum with the frequencies, right, the summation of f y G I of y, where y is exactly that set of y's such that H I of y is equal to this bucket ID. Okay. So, that is expectation of y I. So, it might look a little complicated now, but it is going to simplify itself very soon. Okay. So, let us separate out two terms. First of all, we know that this sum has the element this sum has the element x. This sum has the element x. So, let us take out the element x, right, and if you take out the element x, you will get a term of the sum that looks as follows: G I of x squared f x plus, and now the sum is over x not equal to y, and so on. Okay. So, by linearity of expectation, let us calculate the expectation of this, let us calculate the expectation of the second part. Okay. Let us take this one first. So, what is G I of x? So, see, f x is a constant, there is nothing to worry about that. And what is G I of x squared? G I of x is only plus 1 or minus 1. So, therefore, G I of x squared is always 1, right. So, therefore, the expectation of this part is exactly f x, right, which is what we have written here. Okay. So, that is nice. Now, what is the expectation of the second part? Of the second part, which is the sum over all x not equal to y, right, this quantity, sum over x not equal to, whereas you take the sum over all x not equal to y, right. So, might seem complicated, but again, so just look at this very simple observation, that now that because x not equal to y, you have G I of x and you have G I of y, right. So, the g's are independent of the h's, the value, the g hash functions are independent of the h hash functions. So, therefore, right, whatever else you will have this expression, right, for each term you will have an expectation of G I of x times G I of y, right. But now again G I of x is independent of G I of y, and each of them have 0 expectation, right. So, the expectation of this is 0, the expectation of this is 0. In fact, the expectation of any one of them is 0, and that is enough, right, which means that this entire sum has expectation 0 for every y not equal to x, right, and so the entire sum has expectation 0, because each term has expectation 0 for each y not equal to x. So, this seems somehow it all sort of boiled down to giving me the right expectation, right, which was the entire point of this of these sign hash functions. Okay. But now what we need to do is we need to analyze the variance in order to bound the error, and this is where the independence of the hash functions will come in. Well, they have also come in. We have also kind of used the independence in sort of saying that the expectation of g I f x is g I f y, but that is the independence of the different hash functions, right. Now, what we are going to say is that the fact that whether h, I mean, so you need to know that there are two kinds of independence here, whether h 1 and h 2 are independent, and whether h itself is chosen uniformly at random, I mean a completely random hash function, right. Now, in the analysis of variance, right, you need to, I mean, here we will assume that h I is being chosen at random, right, and there and we will see that we can relax that to make it only something like 2 y is independent or 2 y is universal. Okay. So I won't do the entire variance calculation because a lot of it is algebra, but what you can say is that the variance of y I is going to look something like this. You are going to have summation y f y square, summation over all minus f x square, okay. And right, and we will not use this exact form. What you can use is a simplifying form that tells me, I mean, that goes as follows, that you sort of upper bound this quantity by the 2 norm of the frequency vector f. So, this is the 2 norm of the frequency vector f, and you can upper bound this quantity, and you can upper bound the numerator by this quantity, and the denominator you get a 1 by d, right. You get a 1 by d because I mean in the denominator you get a d because that is the range of the hash function, right. So, implicitly the probability of any collision is 1 by d. Okay. And once you do, I mean, this analysis of the variance is fairly simple, I note. You just need to boil down, I mean, just need to write down expectation of y I square, right, and distribute that, distribute the square over the sum and so on, and we will get this. That is very simple. But once we have this bound on the variance, now we can apply Chebyshev's inequality, because we know the expectation of the random variable is exactly f x, which is what we want. We know a bound on the variance, and let us apply Chebyshev's inequality, which is what we will say that the probability that y I minus f x absolute value of that is bigger than epsilon times the 2 norm of the random epsilon times the 2 norm of the frequency vector is less than equal to the variance divided by epsilon square 2 norm square, right, and we have bound the variance as f 2 norm square by d. So, therefore, you get a f 2 norm square by d divided by epsilon square f 2 norm square. So, therefore, the f 2 norm square cancels out, and then you get a 1 by d epsilon square in the probability bound. So, now we can set, I mean, remember our choice of d, right. So, in reality you would choose d only after seeing this expression. That you see this expression and then you say that okay, it makes, I want to make this probability less than 1/3. So, let me go ahead and choose d equal to 3 by epsilon square. Okay. That says that each y I lies within f x plus minus epsilon times the 2 norm of the frequency vector with probability 1/3. Right. But what are we doing? We are taking the median of these y i's, right. And now what you can use is the same median trick that we have been doing before, and that will tell you that the probability that the median lies within, the probability that the median does not lie within this f x plus minus epsilon, I mean, so f x, this is epsilon times f 2 norm, this is The probability that the median does not lie in this interval is less than delta, right, which means that with probability 1 minus delta, right, for any query, for any fixed query x, we get an estimate with this probability. We get an estimate that lies within f x minus epsilon times the 2 norm of f and f x plus the epsilon times the 2 norm of f. So, a couple of related things I would like to point out is that this probability holds for a fixed query, and this is always the case when we are dealing with these, when we are making these statements, right. If you have to answer for all queries, you have to take a union bound, right, which is not what we are doing here. We are answering for a fixed query x, right. If you have to answer 10 queries, you have to take a union bound over 10 queries. And what is the space that we need? See, the size of a data structure is 1 over epsilon square log 1 over delta, and in each of the positions we are storing a counter. So, it is 1 over epsilon square log 1 over delta times log n. So, that is the data structure that we have. Okay. So by now we have seen at least 4 of these algorithms. In fact, we have seen a variant of CountMain, so I will not talk about that. We have but we have seen 4 algorithms that each sort of answered the question of frequency estimation, right. And these 4 algorithms are slightly different from each other, and therefore it is very useful to kind of get an overview comparison of them. So, this excellent table is from the lecture notes of Amit Chakrabarty. The 4 algorithms that we have seen are Mishra-Gries, space saving, CountMean and CountSketch, right. So, the first column contains the bound f hat x minus f x that we have proven, right. So, the 2 notations that we have used here is that when we say f, the 1 norm of f, that is nothing but summation f x, right, which is basically equal to m, the length of the stream, right. When we say the 2 norm of f, that is equal to the summation f x square over all x, right, that is what we just saw, the square root of that. Okay. So, f 2 norm okay. And see, now you start noticing the trade off that we are having. Both Mishra-Gries and space saving, both of them use only 1 by epsilon counters, let us say actually 2 by epsilon counters. Okay. Both of them are deterministic, so they are excellent, but they only work for insert only streams, not for inserts and deletes. CountMean has sort of has a bound that is similar to that of space saving, right. However, it uses a little more space, right. It is randomized, so it has some error probability. These two are 0, error probability 0 because they are deterministic, right. However, CountMean can also be used to answer some more general queries. We did not really talk about that, and it also works for inserts only. However, if I were to change the CountMean to CountMedian, right, we would get a similar bound here. We would get it would have been minus epsilon times 1 norm of f and epsilon times 1 norm of f, and it would work both for inserts and deletes. CountSketch gives you error bound in terms of the 2 norm of the frequency vector, right. So, remember that the 2 norm of the frequency vector is actually a little bit smaller than the 1 norm, is potentially smaller than the 1 norm of the frequency vector. Okay. And but it takes a little more space also. So, now the space bound is 1 by epsilon square, depends on 1 by epsilon square rather than 1 by epsilon for the other algorithms. It works nicely for both inserts and deletes. Okay. So, this is an interesting trade off, and it really depends on your use case as to which of these algorithms really performs the best. Okay. So, just to summarize, in this lecture and in the previous one, we talked about CountMean and CountSketch to answer point queries about frequencies. They are really 2 user defined parameters. Both of them are dependent on these, epsilon the error parameter and delta the probability bound. Right. Both of these are linear sketches, right, and this is very effective because they now they can be combined across distributed streams. Remember the setting that we are talking about, that suppose you have two data streams, one on machine 1 and the other on machine 2, and you don't somehow you want to combine the statistics across these two streams, right. Because you have these sketches to be linear, you can easily combine these statistics, and that is not so true if you have these counter based sketches. Okay. This is the extension, this is one of the advantages that CountMint gives you over let us say space saving, and or Mishra agrees. CountSketch can handle departures naturally, but for CountMint we need to consider median instead of minimum. There are other extensions to handle range queries and others, and the actual performance of any of these algorithms is much better than the theoretical bound. There have been some efforts to analyze these in terms of saying that if you have a power law distribution, if the distribution is very skewed, it is known that it can be proven that a lot of these algorithms perform a lot better. The hardest instance for these algorithms is when the frequency distribution is more or less flat. It's more or less flat, but there is only a small number of when the heaviest is only slightly bigger than the average, right. If the heaviest are really bigger, much bigger than the average, then all of them perform really nicely. Okay. So, again just the same set of references for our for this lecture, and which are the lecture slides by Graham, as well as the lecture notes by Amit and Graham. So, that is it. Thank you.